The units is kind of fundamental to any engineering course or any engineering system, right? When you're talking about some measurable quantity, you want to specify the units. So the way this goes is we typically specify base units, something which we are going to set up uh, the the basic scale in which we measure certain things. And once those things are specified, we can derive some other things, quantities, which are functions of those base units. So for example, one common base unit is we choose mass, length, time. So let's just use M for it. Let's not specify a specific unit, L and time. Okay. Now, if you want anything else, you would define a new quantity, let's say force. Okay, then you can actually figure out the units of force, which is a derived quantity in terms of the base unit. So force, example is force F. And the way to do this is to think of the simplest thing you can think, which involves force. It could be, I can think of as mass times gravity. Okay, and then we can set up the units so that units of that is the units of mass is, well, we use M here. G is length per time inverse squared, or if you like to see it this way, it's fine, 2L divided by T squared, which is M L T minus 2. So now we have a measure for force in terms of our base units. Alternately, you could define a base unit in terms of force, length, and time. So let's say that our base unit is in terms of force, which will denote by F, length, which is L, and time, T. In this case, mass doesn't really have its own unit. It can be derived in terms of these units. So we know that mass is force divided by gravity. In this case, force is F. Gravity is length per unit times squared. So we have F L inverse T squared. Okay, so those are the derived units for mass. So the choice for using base units is the same. You can't you can't use force as well as mass, as that would be meaningful, not meaningful, right? Because then they are related by G, which is also sorry, L and T, which is also a unit. When you have three things, you can typically or four things, you typically define units for three of them, and the fourth is derived in terms of the three. Now, the way we like to measure things is to have a internationally accepted system of units, and everybody uses the same system. So when we talk about measurable quantities, we use that unit system, and that system is a better way of talking about measurable things. So there are three systems in use. First one, which is not very common in the US, but elsewhere, is the SI unit, or the International System of Units. Okay, it's abbreviated as SI. Here, well, it's also known as a metric system. here our base units are M is for, well, M mass is represented using kgs, length using meters, which is denoted as M, and then time is in seconds, which is S. Okay, so once you have decided these units, you can now specify units for force. So force is mass times gravity. So mass is now kgs. Gravity is has length is length per time squared. So it's meter divided by second square. And so the units for force in SI units is kg meters seconds square. So this is often known as newtons or denoted by N. The second unit, which is more popular in Britain and also in the US, is the British system. It's also known as the foot pound second system, or FPS. Here the base units are as follows. For mass, it's usually pounds. For length, we have feet. And then for time, it's seconds. Actually, hold on. It's so actually they don't really go with mass. They actually specify force, and that's LBF. Okay, so force, and I'll come to what that means in a bit. But if you want to then derive units of mass, so let's derive mass is force per unit, well, F divided by G. And so force is LBF, gravity is feet per second square. And so this is going to be LBF feet inverse second square. So this quantity here is called as slug. So slug is the unit for mass in the FPS system. Okay, so this is something to remember, that it is not mass which is used in the British system. And then the last one is sort of derived from this, very similar to this. It's the inch pound second system, where we replace. So the last one, third one, is inch pound second system, or IPS, where the base units are force which is still lbf. Length is inch and time is second. So if you want to derive the units of mass, you'll say force divided by gravity. Force is lpf. Gravity now is going to be in terms of inch per second square. And so that's going to be lbf inch inverse second square. And that quantity actually doesn't have a name like it does. It's called slug in FPS. So those are the three different ways in which people normally define measurable quantities. And we'll be switching between the two. Sometimes we'll be using the SI, sometimes the FPS, the British system, which is actually more common in the US. So now if you want to look at weight in different units, different systems, in SI, gravity is 9.81 meters per second square. And so if you want to find the weight, that's mass times gravity, which is equal to, well, mass, let's assume that mass is 1 kg, gravity is 9.81 meters per second square. And so the value for weight of, say, 1 unit, in this case, 1 unit is 1 kg, is 9.81 kg meters per second square, which is also denoted as newtons. If you want to do the same calculation in FPS, now gravity here in this system is 32.1740 feet per second square. And we usually like to round this up to 32.2 feet per second square. So if you want to look at the weight of 1 unit in that measure, so in this case, 1 unit is 1 slug times 32.2 feet per second square. So the answer is 32.2 lbf, because the units of force in FPS is lbf, or pound force. And then finally, IPS, gravity is 386.088 inch per second square, which is normally rounded to 386 inch per second square. And so the weight, which is mass times gravity in this unit, is 1. Now there's no slug here, so it's lbf second square inch inverse times 386 inch per second square. And so comes out to be 386 lbf. So you can see that the units seem to be the same between 3 and 2, just that they are, one of them is IPS, one of them FPS. So if you mess up the name, then one of them is going to give you absurd results in the other system, right? So when you say 386 lbf, you have to say it's in IPS and not in FPS. So rarely that unit is used, but it's normally the first two, SI and FPS, which are used. And we'll switch between those two, as I said. Okay. Okay, let's move on to the final part of this chapter. Again, significant figures. So what are significant figures? Well, when you write a number, like say, for example, 1.2 or 3.14 or 76.0, then the number of digits you show up there on in the number are your significant digits. That's two significant digits, two significant. Same for the second one. Sorry, second one is three significant, my bad, two significant figures. Three. Okay, so the number of digits you show up is the significant figures. And so when you're communicating with somebody else, you need to decide, it's kind of important to decide the number of significant figures which you'll be using. You don't just put like 10 significant figures. So in design, in this course, we will stick to three significant digits. Three significant okay, unless stated otherwise. Okay, so if I show you these numbers, 1.2, 3.14, 76.0, which I just copied from the earlier one, it is to be understood that all those numbers are three significant figures. So the first one does not look like three significant figures, but the moment I say that in the course, you should interpret that as 1.20. Okay, it's not a 5, it's not a 4, but it's 1.20 because I omitted the third digit after the second digit after the decimal. Just means that 0. That's how you interpret that number, which is shown as two significant digits. Now, the question, well, we are going to use three significant digits, but when you're doing calculations, you better be careful about how you do the calculations. You're not allowed to truncate significant digits to do calculations, because if you do so, then you'll end up with errors. The significant digits is only to communicate the final answer. So let me just put it down and show you this with an example. So to be accurate, use full or maximum accuracy in the calculation, but only report three significant digits in the final answer. Okay, so an example is this. Now we know the circumference of a circle is given by pi times the diameter. Now let's do this calculation in two ways. One is, well, first let's choose a diameter. Let's say it's 0.4 millimeters. And of course, that's assuming that's three significant digits, so it's 0.40. Now let's do the following calculation. So let's do it as 3.14, 3.1, which is two significant digits, times 0.4. Okay, and the answer comes out to be, I just have it here, 1.24 mm. And then let's say that you're supposed to report this, in this case, up to only two significant digits. Reporting only two significant digits. Okay, that's why in the first place we truncated the value of pi from 3.14159, all that is, to 3.1. And so we ended up with 1.24 and we rounded to 1.2. However, if you use the full accuracy, so this is full accuracy. That is, if you use a calculator and print pi, then it comes out to be up to, I think, 9 significant digits, 3.141159, and so on. Then you will get something like 1.256 mm. And then when you round it up, you end up with 1.3, right? Which is now 2 significant digits. So this is 2 significant digits, that's 2 significant digits. The second one was computed with the full accuracy. You can see that there's an error now because of the use of truncation, right? So the percentage error so to summarize, if you use full accuracy, you get 1.3 using significant digits, or just using 2 significant digits. We got 1.2, and so the percentage error is going to be 1.3 minus 1.2 divided by 1.3 times 100. So that's about 0.1, 0.3 times 100, which is about 8%. You can see it's quite significant. 8% error is quite significant in terms of, say, if you're having a clearance fit, right? And if you're off by 0.1 mm, it's likely that a clearance fit will become an interference fit and your design will fail. And so it's very important to use high accuracy in the calculations. Eventually, you can round it up to whatever significant digits you've agreed upon. Okay. The final note here is that there is an implication on the accuracy when you are talking in terms of significant debate. So if I say that, if I say here in this class that the diameter is 0.5 or just 0.5, I say 0.50 because I need to keep it to 3 significant digits, 0.5 mm. That means I actually am implying an accuracy. I'm implying that the accuracy is actually 0.5 plus or minus, so 0.50 plus or minus 0.005, right? And that's because this thing is, as you can see, is in the fourth significant, is reported to 4 significant digits. Right, that's because the way I've set it up is that 4 significant, all my answers are accurate to 3 significant digits. So the accuracy is going to be accurate up to the 4th significant digit, which is what it is there. Okay. And if you do this, then in this case, the accuracy or the percentage accuracy, like I calculated earlier, is going to be 0.005 divided by 0.5 times 100, which is about 1%. So the answer in this case is accurate to 1%. Now, clearly, if that 0.5 becomes 0.05, then it'll probably shoot up to 10%. So it really depends, right? If you care about depending on what, so this 3 significant digits is probably very useful when you're talking about items which are of the order of 0.5 millimeters or so. The moment you go down 1/10 of that, you suddenly see that using this kind of post 3 significant digits is going to make it less accurate. It's going to go from 1% inaccuracy to 10% inaccuracy. And that's because on the numerator, you will still have 0.005, but the denominator will be 0.05. And so it'll be a 10% increase. So this, all these things depends on what calculations you're doing. So if you're doing nano manufacturing, this probably is a bad idea to use 3 significant units. If you're doing meso or macro manufacturing, like what we do, then it's probably okay. Is that clear? Okay, so that basically ends chapter 2, chapter 1, which is an introduction to design. And we'll get into more details of some of these things as we go through the course. Okay, so the next chapter is on materials. And a big chunk of this is actually covered in your earlier class on materials, right? So this is going to be sort of an overview, and we won't take too much time in chapter 2. But I will introduce things as we need in the course. Material strength and stiffness. Okay, so the simplest thing, and this is probably a very famous, or it's a very usual idea, is to understand what is the stress or what's the stiffness and strength of material. So what you do is basically you take a rod, and the rod is made in that fashion. There is a sort of a groove, and that's of a diameter d0, and then it's loaded in tension, pulled. The machine which helps you do that is called an Instron machine. I don't know if you have used one, but you basically pull the material and you keep pulling it till eventually it breaks. And then you try to get an idea of what's going on in the material by doing a plot, which is the stress strain plot. So P here is the external load. Okay, L0 is called the gauge length. So the material here in question is machined to a specific gauge length, and there are different types of gauge lengths, and they are all standardized. Okay, so just depends on what kind of experiment you're running. D0 is the diameter, as you can see, and then sigma is the normal stress. Okay, in this case, the item in consideration is not going to be stressed in shear. It's only going to have a normal stress. So you've seen the formula for the normal stress. It's basically force. In this case, it's P divided by cross-sectional area. So it's this area which you don't see. It's in the plane of the paper. It's pi times d0 squared divided by 4. Okay, so here we are assuming that here, if you take a section here, you cut it. That section is which is subject to force P, and we're looking at the stress at that section. Think of it this way. So when you start pulling it with a force P, invariably it will stretch. So let's say that that's the new length, extension new length of the specimen. Okay. So now, once we have the specimen stretching, we can define a strain, which is, in this case, it's associated with a normal stress. It's called a normal strain. The definition for normal strain is its change in length divided by the original length. So the units of strain is, it has no units, it's dimensionless. So the change in length in this case is L minus L0, origin length is L0. By the way, this is also known as engineering strain. Okay, they normally don't call it engineering strain, but it's also an engineering strain. There's another strain which we'll call about, it's called true strain, which is slightly different from this one. So they just call it strain. Okay, so when you start stretching that material with force P, depending on the nature of the material, you will see one of the two plots I'm going to show. This is the first type of plot where the black line, solid line, denotes how the length changes as a function of the given stress, right? The stress is increasing as you go along the y-axis. The strain is also increasing. So it starts over here. That's when L equals L0 and the strain is 0, and then you keep going. So now so this is from the book. It puts down some of these points of interest, which I've shown there, PL, EL, and so on, and I'll just define them. Okay, so what I've shown here is very empirical. That is, there is no fundamental theory to this. You take a material, you stretch it, you see the plot, and you do it for many materials, and many materials follow this trend, and those materials are actually called ductile materials. And it'll be clear to us what ductile materials in a bit. And then there's another set of materials which show a different curve. They are actually called brittle materials. And so it's a way in which you can classify materials by just looking at the stress strain curve. So PL is called the proportional limit. Okay, so when you stress the material, you can see that this line from 0 to PL is more or less linear. Okay, so that's called the point where this line becomes non-linear. That is basically when the PL, when you mark the point PL. So after PL, the curve becomes, the curve is non-linear. That is, you can fit a straight line from 0 to PL. So if it's a straight line, then you can actually write an equation between stress and strain. So stress divided by strain is E, okay, what is known as Young's modulus. Some people like to use Y for Young's modulus. Okay, and so that's the equation of a line, right? Y divided by X equals constant, and it passes through the origin. And so if you look at Young's modulus for materials, you should find values for them. It's typically for steel, which is usually used for a lot of construction as a construction material. The value for steel is 300 m mega psi, which is a unit for pressure or force per unit area or stress, which is also 207 gigapascal, which is actually a unit in SI system. Stainless steel, which is corrosion resistant, has a slightly lower Young's modulus. So it's 27.5 mpsi, or about 190 GPa. Okay, so once we're at the PL, then there's a point called EL, which I've shown here. It's the elastic limit. Uh, at this point, actually after this point, the material starts becoming plastic. What I mean by that is the moment you let go the force, it doesn't spring back to its original length. It will deform permanently. Okay. So second point is EL, is also the elastic limit. The material shows permanent deformation beyond this point. Okay, so between PL and EL, which is, recollect, it's just between these 2 points, the material is elastic but non-linear. That is, you cannot use Young's modulus to characterize the material behavior there. Okay, so let's move on this curve. We are to this point, which is Y, and that's called a yield point. So I have it again over here. Y is the yield point. Okay, what's the yield point here? The strain increases faster than stress. Okay, what that means is that up till now the slope was something like that, like it was almost like it was vertical. As you reach point Y, you see the slope decreases, and that just indicates that the strain is increasing much faster than the stress. Sy is called the yield strength, which is the often reported measure on most materials. So you can picture it on that plot then once you have it. Now, how do you actually find this? So PL is easy, right? It's when the system starts becoming nonlinear. EL is also easy to an extent because that's where if you see permanent deformation. It's not clear how to find the yield point. So what people do is they have a method called offset method. To find Sy. So what they do is they define this point A, that A is some percentage of the gauge length. So here's how the offset method is used to find the yield point. So first, establish point A. Okay, and that's just chosen heuristically. Choose point A to be 2%. Okay, and I'm just putting a number there. It could be 1%, 2% of gauge length. The gauge length there was L0. So if you choose a gauge length of 2%, that is 1.002, then the strain at A is going to be the true length, which is 1.002, right? Minus the gauge length. Let's say it's 1, or if you want, you can put L0. If you like, then you can put 1.002 L0, which is the stretch length minus L0 divided by L0. Okay, so other ways. So people also use 0.1, 0.01, and 0.5% for A. So once you found the strain, now draw a line with slope E at point A. Okay, so once you found this point, which is at 0.002, this line has a slope of E. Draw a straight line passing through A, and that line, when it intersects the curve, is your point Y. Okay, so the point of intersection of this line to the curve gives Y, and you're done. And does SY. So this is find strain at A. This one draws the line. So the line equation would be E times A, and then intersection. Section to get SY. So those three steps gives you the yield point and hence the yield strength. Okay, so we see that that's Y. Then we have this point. This is sort of the apex of the curve. So this is where the slope of the line is almost zero. And then ultimately the material fails here. So it sort of breaks. This is the ultimate or max strength. In other words, it cannot take a stress more than the maximum strength, which is that point U. So let me put this in the notes. So we have U, which is, that's number 4. U is called the ultimate or maximum strength point. Okay, we'll denote that by S U for S ultimate, or S, I think it's also called SAT. I'm sorry, it's SUT. UT for ultimate strength, ultimate tensile strength. Okay, and so you can see that at U, it will actually went downwards, and the final F is when the failure takes place. Fracture or okay, so that's the curve for a ductile material. There's another type of material called a brittle material, where the curve looks something like this. Okay, so we had those points, we had EL, PL, which are also true for this one. They have not been shown. There's a yield strength, which can be computed by the offset method by finding this point A, which is again by heuristic. And then you can see something interesting, which is the curve, previous curve. If you look at this curve, there was an ultimate strength or where the strength was maximum was different from the point at which it failed, right? There was this whole strain where it was still bearing the weight before it failed. But for a brittle material, that's not true. The point at which the ultimate strength occurs and the point at which it fails is the same. At U, the material breaks so that U and F are the same point. Okay, so the question is, which of the two materials would you use in construction? Would you use the brittle material or ductile material based on these two curves? Can't hear you. Ductile. Why would you use ductile material? What if I told you that they have the same ultimate strength, the ductile and brittle material? In that case, which one would you use? Yes, so right. So the reason why you would use the ductile material is that it actually gives you a warning before it breaks, right? And the warning is something that just, yeah, so the warning occurs here, right? Right here, it tells you that the strength is the ultimate strength, and then it goes downwards, which means that now the stress, the load-bearing capacity decreases and the strain keeps increasing, while there is no such warning for a brittle material. It just fails. And so before something catastrophic can happen, you can actually do something about it. So I'll just put it down and I'll let you go on over time. So ductile materials show signs of failure and hence are preferred over brittle material. Okay, so